Okay. A projectile is shot at a hill, the base of which is 300 meters away. The projectile is shot at 60 degrees above the horizontal with an initial speed of 75 meters per second. The hill can be approximated by a plane sloped at 20 degrees toward the horizontal. The equation of this straight line is y equals the tangent of 20 degrees x minus 109. Where on the hill does the projectile land? The first thing we need to do is draw a diagram and make sure all the parameters are labeled using the given information in the problem. So if we draw our diagram, we label our parameters, the initial velocities in the x and y direction, the time, the change in position in the x and y direction, as well as the acceleration. So as you can see, we took the information from the problem, the 300 meters from the projectile shot to the hill, the 60 degrees above the horizontal, the 75 meters per second drawn as a vector in blue, the hill, which shows 20 degrees above the horizontal, with the following equation, the y equals the tangent of 20 degrees x minus 109. So what is the problem asking us? It's asking us where on the hill does the projectile land? To do that, we're trying to figure out the change in x and y. Since they're two components of it, we have the distance to the hill, but that information is not that relevant to us right now. So we'll try to use this motion equation. The change in y equals the initial velocity in the y direction times time minus 1/2 gravity times time squared. Now, we don't exactly have a time component, and we don't have the initial y component. So if we think about it for a second, we can take this vector and we can break it up into its components since we're missing some information. So as I had mentioned, we're going to break it into the components. We're going to get the x component, which is the initial velocity times the cosine of theta, which comes out to 37.5 meters per second. And then to get the y component, we do the initial velocity times the sine of theta, which is 75 meters per second times the sine of 60 degrees, and we get 65 meters per second. So we'll substitute that into our equation to see what kind of information we can get. And I already know that we don't have time. So as we substitute this in, we end up getting this equation remaining at the bottom. The 0.36x, which is the tangent of 20 degrees in the calculator, is what we got. And plugging all the information, we're still kind of unsure. So is there a way we can possibly solve for time? Well, there is. We can use another motion equation with information that we do have. So we know the change of x equals the x initial plus the initial velocity of x times time. Using this information, we get some value for time. Not an exact value, but we might be able to use this information that we have. So t equals the change of x times 37.5. Now what we do is we can substitute that value in for t into the original motion equation on the bottom left, the one that we worked out and simplified, cleaned it up a little bit. And if you plug that in, you're going to get 0.36x minus 109 meters, and you times and multiply everything out. Some stuff's going to cancel, and then you're basically left with a quadratic equation or parabola. It looks like it would be a parabola. So we could just use the quadratic formula. And when we do that, we get 459.74 meters. Now that we have that x value, if you look back at our original equation, the y equals tangent of 20 degrees x, you can just substitute it in, and it will solve and give us our final answer. So on the hill, it is 56.5 meters above the horizontal on the hill. That's where the explosion happens. I hope this was informative. Thank you.